My name is Jorge Jimenez, and I am a power electronics engineer focused on firmware and converter design here in Power Smart Control in PSC. So as Marco said before, today we're going to delve into one of the critical aspects of power electronics, that is the validation of the control algorithms. We have to consider key aspects such as efficiency and time to market. And here in PSC, we have developed a methodology that eliminates the uncertainties that can exist between the simulation environment and the experimental validation of the power converters. So as you have seen before, the SmartRCP is a rapid prototyping system that can be used as a key tool to develop and implement the control and safety algorithms of a power converter. We will explore the control structure of a dual-active bridge converter. We are going to configure the experimental environment in Vivado. And most importantly, we are going to see how real-time simulation, or RTS, allows us to test the entire operation range of the system of our converter, as well as critical scenarios, so we can see if the alarms or our systems behavior properly, without the risk of component failure before moving to the real converter prototype. So moving into the technical aspects, this slide shows you first the electrical diagram of the dual-active bridge, and also the control architecture that we are going to use today. It consists of a PI regulator whose function is to maintain a specific input current in the input port of the converter by modifying the phase shift between the triggering of the primary bridge and the secondary bridge of our converter. To apply this phase shift to the trigger signals, we need an IP core, the phase shift modulator that allows this shifting in order to trigger a transistor based on this delay, that is the output of our PI regulator. In our case, to close the loop, the current measurement required by our control can either come from the real converter through a current sensor, or from the real-time simulation model. So it allows us to validate our control with either two of the available options that we have in this case, and we are going to see today. These slides shows you the laboratory setup for today's webinar. On the left, we have the control stage that is composed of a SmartRCP and a laptop, a personal computer, integrating the user interface. And on the right, we have our device under test, our dual-active bridge converter. It's a 50 kilowatts prototype that we have designed here in PSC, in Power Smart Control, by our engineering team. This image also displays the main components of the converter, for example, the DC bus, the power PCB, the magnetics, and all the passive secret protections, etc. And also here you can see the main specification on voltage, power, and switching frequency of the unit. We chose the dual-active bridge for this demonstration because it's one of the most demanding and versatile topologies in today's market, because this is ideal for DC microgrids and EV charging, thanks to the galvanic isolation and also because of the bidirectional flow of the power. However, this type of converters requires a control with an extreme precision in the phase shift management that is very challenging for any control system and for any control board or rapid prototyping system. So the validation methodology that we will follow is divided in two main phases. First, we are going to run our control model against the virtual plant of the converter, the RTS, within the SmartRCP's FPGA. All the model parameters, the inductance, sense ratio, DC capacitor, must be selected according to the real parameters of the real converter. As we said before, at this stage, there is no risk of error because everything is simulated, and the user can perform all the necessary tests and check if everything is okay and it looks good through the PL data logger. That is the data acquisition tool that we have developed for our user interface. It's like a digital oscilloscope with great precision, with a high precision around 20 nanoseconds of time step. So once we have checked that our control is validated and works properly, the second stage is to control our prototype with the SmartRCP. And then we can analyze the waveforms with the PL data logger tool or with using physical oscilloscopes and current and voltage probes, as we are going to see in the live demonstration. In order to implement the control on the SmartRCP FPGA, we are going to use Vivado. That is the tool that EMD provides in order to program the FPGAs. In this capture, we can observe two fundamental parts of the template that we provide. The first is all the generic drivers and stages that the SmartRCP requires to operate. For example, the registers that came from the user interfaces, the ADC drivers, the inputs and outputs drivers, the register that we can send from the FPGA to the interface, the PL data logger IP, and the PWM IPs to control the actual power converter. And the second part, that is the part that we are going to see today, are the dual-active bridge RTS IP. So the IP that enables the simulation of the converter inside the FPGA in real time, and also the control IP that integrates the phase shift control in order to operate our converter. Delving into the details of the control IP, here is the aspect that the IP has on Vivado, and the main purpose of this IP is to generate the trigger signals of each transistor to establish a specific value of current in the input of our converter. So we can read, as we see at the beginning of the presentation, the input current from the ADC or the RTS. It's going to compare this current with a reference. It's going to pass through a PI regulator that we can parameterize, and then we have the modulator to establish this phase shift between the trigger signals of the primary and the secondary bridge of the converter. I'm not going to stop about in this slide, but well, here we have this is available in our documentation, but we have here the description both for the input and the output signals of our IP. For example, here we can see that we have a main alarm signal. We can change the operational mode of the IP, and then we have the input of the measured current, the reference current, etc. But this we are going to cover in more detail later on the live presentation, live demonstration. Sorry. And moving to the converter model, this is a physical model that solves all the differential equations of the simulation in real time. It emulates everything since that we can see in this diagram. Input and output capacity DC filters, the inductor, the single phase transformer, as well as each of the transistors of both bit sets. All the simulation parameters, the inductance, the capacitance, the times ratio, etc., can be modified in real time from the user interface in order to make variations or to adapt the model to the real converter. The output of this IP core of this function will be the input and output current, the AC voltage imposed by the primary and the secondary bridge, and also the AC current that flows through the inductor. So the performance achieved with the IPs is covered in this slide. And with the IPs developed for the SmartRCP, we can achieve 20 nanoseconds for the real-time model, which is industry leading for this type of devices and essential for simulating converters operating at switching frequencies around tens of kilohertz up to 100 kilohertz. We also have 5 nanoseconds PWM resolution, which is vital for currently operating the phase shift. Which is vital for currently operating the phase shift between the bridges of the dual active bridge converter, and finally the response time of the calculation time of the regulator is going to be around 5 microseconds. That is time short enough considering the sample time of the ADC conversions. So the summary of this is that we can deliver high performance capability for power converters with a high switching frequency, or at least switching frequencies around the tens of kilohertz. So in this slide, we can see the IP connection diagram of the FPGA, because everything that we are going to see today is programmed in the FPGA of the system on chip. As you know, the system on chip is composed of 2 parts. The first part is the microprocessor of the processing system, and the FPGA, or the programmable logic part of the device. So first, we will have the user interface, the SmartRCP user interface, where we can control and parameterize everything that we have in our firmware, both for the control side and the real-time simulation side. We can start and stop the operation of the converter, and we can see the error signals and then everything from the firmware side, from the SmartRCP side. As shown here, the control IP can be operated both from the current measured from the converter, and also the control can be operated with the current that is being simulated with the real-time simulation model. And all the control signals and the simulating signals can be seen in detail using the oscilloscope or the PIA data logger IP that we are going to see in more detail in the live demonstration. So our workflow for the live demo will be, in the demo we will show 2 scenarios. In the first one, we will validate and evaluate the control only with the RTS model. So the power converter will be turned off. And then we will control our converter prototype using the same IP that we previously validated in the first stage. So as mentioned throughout the presentation, the entire process can be controlled and monitored using the RCP interface tool that also includes the PL data logger visualization suite that we also are going to use in our workflow for the validation of the convert. So okay, let's start with the live demonstration. I'm going to change this. So, okay. This is Vivado. As said before, this is the tool that Xilinx or AMD provides for the programming of the FPGA of our system on chip, the system on chip that the SmartRCP includes inside. And here we can see all the basic drivers and IPs that it includes in order to operate the SmartRCP properly. For example, here we have an IP that establishes the input and the digital input and outputs. We have here the SmartRCP interface registers that can be sent through the laptop through the SmartRCP. Here we have the IP that enables the ADC conversion, and also another IP in order that enables the RMS and average calculation for the user interface. We have here the IP to export the trigger signals of each transistor, the PL data logger IP, and finally an IP to read register for in the user interface from the SmartRCP firmware. So this is the basic template, and over this template we are going to configure everything to be able to control our tap converter. In order to do that, it's very simple. First, we are going to include the control IP that we have seen in the presentation. I'm going to put it here, okay? And here we can see all the input and outputs that we have seen before. The first thing that we have to do is click here to run connection. This is going to automatically connect all the clock signals of our IP. And then we have to connect to the rest of the template of the environment, each of the inputs and each of the outputs of our IP. As we can see here, the first thing that we have to connect is the main alarm. This alarm is going to trigger in the event that any of the measured voltage of core or currents variables exceeded a certain threshold. That threshold is configurable through the user interface. So we are gonna connect this input with the main alarm signals that came from the ADC RMS IP. And we have to do the same with each of the inputs. The majority of them are going to be controlled by the user interface. For example, this one is going to establish the operational mode of the IP. So we are going to connect this one. I'm going to move it here. We are going to connect this input to the output user register IP, so we can change the value of this variable in the user interface, and we are going to move to each of one. For example, this one is the main user enable signal that is going to enable the operation of this IP from the interface. We are going to connect now, as we can see here, the input current, but the one measured from the ADCs, from the current sensor. So we have to move over here and connect the input current that we are measuring here in the ADC block to our IP. As we can see here, the next signal is the input current, but the one measured with the the one obtained with the RTS model. So we are going to connect this signal later, and I'm going to move on to the rest of the signals that we have here. The next one is the reference current of the loop, the proportional gain of our PI regulator, the sensing mode, the integral value, integral gain, the dead time of that we can establish the dead time of the triggering of the transistor of each leg of our converter, the limits of the output of our PI regulator. We can also change the operational mode of this IP between closed loop and open loop. So we can change the phase shift of the triggering of each bridge of the converter with this value, okay? And finally, we have a configurable slew rate for all the references, and also we can change the switching frequency of our converter. So all the inputs are connected to our template, and now we are going to move on to the outputs of our template. So the main thing that we have is the triggering signals of each transistor, to our PWM signals. So we are going to connect these signals to the PWM IP core. So I'm going to move our control to over here to see it better, and we are going to connect the trigger signals of each transistor to our IP in order to be able to control our converter prototype. So now that all the trigger signals are connected, we also have a couple of variables to see how the control is behaving. The first one is the current reference that the control is currently using in its control mode. It can be the ADC one or the RTS one. So we can see if we have the capability of see the value of this signal in the user interface. So if we want to see that in the user interface, we have to connect it with the input to user register IP. And also we can see which the value of the phase delay of the control, the phase delay that is being applied to each bridge with this variable. So also, if we want to see how the phase delay is evolving through the operation of the converter, we can see the value in real time in the user interface if we connect this signal to this IP. So both the input and the output of the control IP is connected, and we are with this scenario we are able to control our converter. But let's imagine that we want to check first if this control IP is going to work properly with our system. So for that, we are going to use our real-time simulation model in order to validate and check that the behavior of our control is okay for the specification and for the environment that we want to use. So it's very simple. You have just to search for the IP in the library that we have available and load it into our Vivado project. And then the procedure is very similar than with the control IP. The first thing that we have to do is click on Run Connection in order to connect automatically all the clock signals to our IP core. And now we are going to connect first all the input signals and then all the output signals of our IP. As we can see here, the first group of signals that we have is the variables that parameterize the capacitance of our filters, the inductance of our coil, the serial resistance of our coil, and also the parasitic or the serial resistance of our voltage sources. So as these variables are, we want to change it in real time with the user interface, we're going to connect it with the output registers IP, as well as we have done with the control IP. So we are going to connect all of them to the control IP. So, and much as a real converter, the RTOS model is going to depend also on the triggering signal of each transistor to operate. It's going to be like a real converter. So the operation of the control IP is not going to change if we use the RTOS model or the real converter. So we are going to connect all the triggering signals of each transistor to our real-time simulation model. So we are going to go one by one, and we're going to connect all the signals to our real-time simulation. Okay. So the last group of signals that we have is the input voltage of the model, the output voltage of the model, the enable signal, and the transformation ratio of our transformer. So we are going to also connect them to the user interface, and the enable signal is going to be the same that we have used before for our control IP. And then as we have seen before, the last signal that we have here is the input current of the RTOS model. So we are going to connect this signal to our RTOS model in order to validate the operation of the control IP with our real-time simulation capabilities. And finally, regarding the rest of the outputs, the rest of the signals are going to be connected to our PL data logger IP in order to visualize the revolution with the highest precision possible, in order to see if our control is working properly with nice detail. So I'm going to move this over here, and I'm going to connect every signal. Sorry. Okay. I'm going to connect each signal to our data logger IP. So we can see through as we are going to see now, we will be able to see the evolution of each signal, each simulated parameter in the user interface. Also, I also take this opportunity to connect all the measurements captured by the voltage and current sensors, the input and output voltage and the input and output current that is going to be measured through the sensors of the SmartRCP from the prototype to the PL data logger in order to see everything. Sorry. Okay. This is the last one. So as we have seen now, this is all the steps that we have to cover in order to implement the control template or the control IP of the dual active bridge, and how to connect this control IP to our real-time simulation models in order to perform all the validation in a simulated environment previously to the validation of the power converter. The last thing that we have to do now is to generate the vStream. I mean, complete the synthesis and the implementation of all the logic that we have here. And this process takes approximately 30 to 20 minutes, more or less. And this is why we are gonna go through this step, and we have all we have the firmware preloaded in the experimental setup. So I'm going to close this, and I'm going to move the user interface to the main screen. So, okay. Now we have generated the vStream with Vivado. We have loaded the firmware into the SmartRCP through the micro SD card, and we have everything ready to test our control IP. We're gonna do a quick walk around of the user interface. The main things that we can change from here are the parameterization of each channel, of each measured channel, and so we can change the upper and lower limit of the alarm. Also, the waiting time that we want to establish between the triggering of the alarm and the alarm event to go on. We can also change each channel integrates a digital low pass filter, so we can change the crossover frequency of each filter, and we can also change the gain of offset of each channel in order to adjust properly the measure of the ADC converters to the real measure of the voltage of currents that we have on our prototype. Here we have the RCP in registers. This part is equivalent to all the registers that we have here in order to control both the contour and the RTS model. So the exact order of the same order that we have here in the firmware part is the variables that we have here. We have the disable of the period OEM, the control working mode, the switching frequency, the death time. Everything is configured and also can be saved into a parameter file with all the parameters that we want to have in our simulation and in our control states for the experimental setup. For example, regarding the RTS model, we can see here that we have parameterized the input voltage with 175 volts, the output voltage with 100 volts. The inductance value of the coil is 10 microhenries. The serial resistance is 200 milliohms, etc., etc. So each of these values are the same that our prototype have, so we can obtain the same result with the simulated model and with the real converter. And finally, what we have here is the real data logger. So this is like a digital oscilloscope that enables the visualization of every signal that is inside the FPGA in real time and with a very high precision. So we are going to first test the control IP with our real-time simulation model, and we are going to close the loop with a reference of 15 amperes. So we are going to click here in enable, and well, I forgot to mention that here we can configure this section of the interface to see in real time the evolution of the parameters of the register that we have inside the FPGA, and also we can see the measure of the voltage and the current sensors. So what we are seeing here first is the phase delay in degrees that we are applying between between primary and secondary bits of the converter. We got seen here the input current that we are simulating, and here, as said before, the input voltage, the output voltage, and the input current and the input current. So if we enable the oscilloscope, we can see here, I'm going to adjust the trigger, that this is the real-time simulation model, and our control IP is controlling the simulated plant and not the real converter, because as we can see here, the input voltage, output voltage, and currents are set to 0 because the converter is not operating. But we can see how the control plant is able to maintain a specific value, a certain value of current on the input. Now is 15 amperes, and we can also see here, for example, the performance of our control loop. For example, if I change the reference current in my control. So now I'm going to move to 10 amperes, example of what happens if I change my reference to 25 amperes. So we can see in real time how the control is changing the phase shift between the primary and the secondary bridge, because I forgot to mention that this signal is the AC voltage imposed by the primary bridge. This one is imposed by the secondary bridge, and this one is the current that flows through the inverter. And in this plot, we have the DC input current and the DC output current of our converter. So this is very useful because we can do all the tests that we want without the risk of breaking anything of our prototype. We can see what happens. For example, now I have a positive reference, so we have a positive power flow. We can see what happens if I change the current reference to a negative one. So the power flow has to change its direction. So we can see how all the evolution of all the signals that are occurring are happening in real time, and we can test everything, as said, without any risk. We can also change the acquisition period to see more or less of the waypoints. We can change this, and also it's very useful to test the stability of our control loop, because here we have the proportional gain of our PI regulator and also the time constant of our PI regulator. So let's change, for example, this gain to a higher value, and we are going to change the current reference of our controls and see what happens here. And as we can see here, the behavior of our control loop is totally unstable because it's not able to maintain the 5 amperes value of current in the input. And for example, if we change back this value, we can see how the control is stable again. So, as said before, everything can be tested without any risk. So this would be the first stage. We have seen that our control stage is stable and works properly, and everything works fine. And the next step is to do the same, but with our power converter, with our dual active bridge. In order to do that, we have this laboratory setup. We have our power converter that is controlled with our SmartRCP unit, and we are going to use two programmable power supplies at the input and the output of our converter to impose both the input and output voltage and do all the tests with a higher grade of safety, with a higher safety possible. So we can see here the input and output voltage. And for example, here is the user interface of the power supply. And we are going to want to run a test with 175 volts on the input port. So I'm going to turn on our power supply, and we can see here how the measurement of the input voltage changes up to 175 volts. We can also see the value of the reading here. I'm going to change the current limits. So this is the power supply that is connected to the input port, and I'm going to do the same with the output port. So here now the voltage is 0, and I'm going to recharge the output port up to 200 volts. I'm going to change. Okay. So now I'm gonna change my screen because I have a secondary screen here. Okay, can I verify if you are seeing the screen now? The screen?
Yes, we are seeing it perfectly.
Okay, I'm gonna move this over here. The registers over here. So what we have here is both the input and output power supplies, and we have here an oscilloscope with 2 voltage probes and 1 current probe that is going to measure the AC voltage imposed by each. It's going to measure this, the input AC voltage, the primary bridge AC voltage and the secondary bridge AC voltage, and also the AC current that flows through the inductor. So I'm going to do this here, and I'm going to parameterize everything. I'm going to enable the PWM signals, and I'm going to change the sense working mode to indicate our control stage to work with the measured current and not with the simulated one. So we're going to test it directly in closed loop. So we are going to see that we have to achieve a current reference of 5 amperes. So as can we see here, we have a measure of 5 amperes on our SmartRCP and 4.5 amperes in the input power supply because of the difference on the calibration of the sensors. But we can see here how the same waveforms that we have seen before with the model, because we can also see in real time how we can run the RTS models on the same time that the control state. So we can see here the similarities between the RTS model and the current that we are sensing in our converter. And then we can test our control in the same way. We can change, for example, the reference current up to 10 amperes and see how the control stage is able to operate properly our converter. We can change also the reference to 15 amperes, for example, and we can see here that the closed loop operation that we have first checked with our RTS simulation that works fine, it also works without problems with our power converter. We can also check, for example, change on the power flow. So it's going to change from 15 amperes up to down to minus 15 amperes. So we can see here how the waveforms are changing in real time. And in every moment, we can see also that our real-time simulation model that we are running is giving the same result that the one that we are measuring through the sensors, or through, in this case, through the oscilloscope of our converter. So we can see how the workflow of design is intended to be with the SmartRCP platform, and also we can see how the real-time simulation helps in order to perform all the necessary tests of the control without the operation. of the repair converter, and don't take risk in order to break something or break some parts of the converter that is very expensive in time and in money. So that would be all of today's presentation. I hope everything has been clear enough. I'm going to share my screen again. Okay, so thank you very much for your attention. And if you have any question, now is the moment to clarify them.